Do you hear me? Okay. Well, I'm happy to be here and present our paper, which is called Genetic Programming on Program Traces and Inference Engine for Probabilistic Languages. Well, the key idea is the following. Two crucial approaches in AGI are cognitive architectures and universal algorithmic intelligence. These approaches start from very different points and sometimes are even treated as incompatible. However, we believe that they should be united in order to build artificial intelligence that is both efficient and general. However, a framework is required that can help to combine them on the conceptual level and the level of implementation. And we also believe that probabilistic programming could become a suitable basis for developing such a framework. And just query procedures in the Turing-complete probabilistic programming languages can be used as direct approximations of universal induction and prediction, which are the central components of universal intelligence models. And whereas more probabilistic programming has been already successfully used in cognitive modeling. We present a novel approach to inference in PPLs based on genetic programming, which is applied to probabilistic program computation traces. Program traces are used as a universal genetic code for arbitrary generative models, and it is enough to only specify such a model in the form of probabilistic program to perform computations. To the best of our knowledge, there are no works devoted to implementing an inference engine where PPLs are combined with genetic programming. So that is the main contribution of our paper. PPLs provide the possibility to define generative models declaratively without the necessity to manually implement model-specific inference algorithms, replacing them with the built-in generic inference methods. Turing-complete PPLs allow for specifying generative models in the form of arbitrary programs, including programs which generate other programs in some domain-specific language. On the one hand, the performance of genetic inference methods in PPLs can be rather low, even for models with a small number of random choices. These methods are most commonly based on random sampling. Thus, more appropriate inference methods are needed, and genetic programming can be considered as a suitable candidate. On the other hand, wide and easy applicability of inference in PPLs is also desirable by evolutionary computations. Indeed, one would desire to be able to apply some existing implementation of genetic programming simply by defining the problem at hand without developing binary representations of solutions or implementing problem-specific recombinations and mutation operators. Consequently, it is interesting to combine generality of inference in PPLs and strength of genetic programming. Evaluation of a program with random choices in PPLs is performed in the same way as evaluation of this program in a similar non-probabilistic language. However, programs in PPLs are treated as generative models defining distributions over possible return values, and their direct evaluation can be interpreted as taking one sample from corresponding distributions. Multiple evaluation of a program can be used to estimate an underlying distribution. PPLs go further and support conditional distributions. The simplest way to sample from conditional distribution is rejection sampling, in which a program is simply evaluated many times until its condition is not satisfied. will be satisfied. Monte Carlo Markov chains are frequently used instead, and it can be much more efficient than rejection sampling for evaluating posterior probabilities. However, without utilizing some additional techniques, it can be as bad as rejection sampling, or even worse due to the overheads in retrieving the first appropriate sample. In many practical problems, a user can convert a strict condition into a soft one, or even initially have a task to optimize some function. Thus, query procedures which accept a fitness function for optimization instead of strict condition for satisfying can be used as a part of MCMC sampling, as well as they can be used independently for solving optimization problems. Well, since exploration of solution spaces in probabilistic programming requires manipulations with random choices made during program evaluation, development of new query procedures is connected with inferring in the evaluation process. We reproduced using scheme as the host language, some basic functionality of church programming language, including a number of simple functions, several random functions, and so on. And the most distinguishing feature of our implementation is optimization queries. Well, there is an optimization query example, and query expression is x, which value should be found that minimizes the given optimization criterion. In the bottom of the slide, there is a call to evaluation query procedure with the population size of 100, 0.03 mutation rate, and the second 100 is number of generations. Well, more complex models can be written. For example, this slide shows the solution of the subset sum problem. To combine genetic programming and with probabilistic languages, we treat each run of a program as a candidate solution. The source of variability of these candidate solutions comes from different outcomes and random choices during program evaluation. Mutations consist in slight modifications of previously returned random values. The evaluated program can be considered as expanded initial program, but with supplementary information of all random choices made during the evaluation. This program can be evaluated again, and previously made random choices will be taken into account during this re-evaluation. During each following re-evaluation of the expanded program, deterministic expressions are not evaluated again, but their previous values are used. All stochastic expressions are evaluated in the same way as they are evaluated in the first run, except for calls to the basic random functions, as they are modified in order to take previously returned values into account. Well, crossover also utilizes program traces. However, it requires dual re-evaluation of two expansions of a program. These expansions are interpreted together as the same program while their structures match. The main difference is an application of the basic random function, since the previously returned values from both parents should be taken into account. For example, in our implementation, the dual flip randomly returns one of the previous values, and the dual Gaussian returns the value between corresponding values of both parents. Mutations are introduced simultaneously with crossover in the sake of efficiency. It might seem that this approach allows for a simple form of genetic programming for parametric programs only, but this is not really the case, since in functional probabilistic languages, one can easily program arbitrary generative models, including those that generate other programs. The slide shows some simple examples. Using the described mutation crossover apparatus, we implemented evolution query. Well, we considered 3 tasks, each of which can be set both for conditional sampling and fitness function optimization. 3 query functions were compared: MH query, annealing query, and evolution query. We used MH query implementation of the web church, and annealing query and evolution query are our implementations. For obvious reasons, MH query was used to retrieve only one sample. Here are the results for the curve-fitting problem, in which a polynomial should be found that goes most closely to the given set of points. It can be seen that MH query is inefficient here, and evolution query is the most precise, while annealing query works correctly, but it converges slower. And the worst precision is achieved when the number of parameters is selected incorrectly. Well, one more test task we considered was the task of integer number sequence prediction. We restricted the set of possible sequences to polynomials, but it can easily be extended to the wider class of sequences defined by recurrence relations. Examples of sequences are presented on the slide. The same generative model was used in all types of queries. We ran tests for different sequences and compared the results. MH query wasn't able to find a solution in each run. Depending on the web browser, it either finished with the maximum call stack size exceeded, error, or worked extremely long in some runs. Annealing query and evolution query also were not able to find precise solutions in each case and terminated with imprecise solutions. Percentages of runs in which correct solutions were found are shown in the table. MH query yielded surprisingly bad results here, although its inference over other recursive models can be successful. Evolution query also yielded slightly worse results than annealing query. The reason probably consists in that this task doesn't decompose in subtasks well, so crossover doesn't yield benefits. But annealing can approach the best solution step by step. And in conclusion, we developed the method of simulated annealing and genetic programming over probabilistic program traces. For the best of our knowledge, that is the first implementation of such methods. The same functions for genetic operators over program traces were used to solve optimization problems for very different types of objects, including parametrically defined function sets and symbolic expressions without producing invalid candidate solutions. It will be interesting to combine probabilistic programming with advanced genetic programming systems such as Moses. In spite of simplicity of the used meta-heuristic search methods, they outperform the standard MH query. Although this comparison doesn't mean that annealing query and evolution query can replace MH queries, and they solve different tasks. It shows that they can be combined, and also optimization queries can be useful to extend semantics of PPLs. Still, efficiency of general inference methods is insufficient, and this could be one of the principal obstacles in the path to AGI. Possibly one general inference method cannot be efficient in all problem domains, so should be automatically specialized with respect to each domain encountered by an AGI agent, implying that such methods should be deeply combined with cognitive architectures. Thank you for your attention.